Hello, and welcome to another pre-calculus lesson with Professor Checo. Today's focus is going to be lesson 3.3, future value on annuity and sinking funds. So let's get straight to it. Take a peek at these questions. And here we have 18 questions, looking good. So let's go to the first one and let's see what the textbook says. Get more help, go to the textbook. Alright, so an annuity is a sequence of equal periodic payments. If payments are made at the end of each time interval, then the annuity is called the ordinary annuity. We consider only ordinary annuities in this book. The amount or future value of an annuity is the sum of all the payments plus the interest earned. So, awesome. Looks like we're going to just have like a sequence, and then it's probably going to come up with a formula, conceptual insight. Feel free to read that. All right, so here is our future value of an ordinary annuity. So it's your future value is equal to your periodic payment times 1 plus your rate per period raised to the number of payments minus 1 divided by the rate per pay period. Okay? And you just plug it into the equation and got it. So it's going to be like a, okay. Balance sheet, making values, sinking funds. This is like a slightly different formula. Oh, because we're trying to find the payments using the future value. Okay, just working backwards. Cool. Sorry. Should I scroll down? No formulas, no formulas. Cool, cool, cool. All right, so looks like a very formula-based homework section. So I'm just going to maximize this. All right, so let's see. Find the sum of the first 13 terms of a geometric sequence below. So now all we need to know is how much first geometric is being multiplied. So I'm guessing they're going to give us a formula where it's A of n. Yep. So this is the geometric sum formula where you would just plug the first term times 1 minus the rate times the number of terms, all divided by 1 minus r, which is the rate ratio. Okay. So now here, to go from 2 to 6, from 6 to 18, from 18 to 20, 54, it would be 3. So it would be my first term, 2, times 1 minus 3 raised to the 13, all divided by 1 minus r. So for here, what is the multiplier? 2. And you're looking for the 10th term. So then you would just plug it in. Boom. Solve it and get an answer. Cool. Okay. That's the first one. Determine the sum of the first 6 terms of the geometric sequence where a is equal to 2 and r is equal to 4. Again, the same exact formula. Plug it in. Everything was given to us. We're looking for the first 6 terms. Cool. Moving on. Determine I, the rate period, and n, the number of periods for an following annuity. Quarterly deposits of that are made for 9 years into an annuity. All right, let's try to figure this one out. Now, find I is the rate divided by m. So that should be 0.065 divided by quarterly should be 4. So I'm going to say I is 0.1625. Oh, it should have been 0.0. My calculator didn't take it, so then there should be a 0 right there. Type in integer. Is I is that number, which is that divided by compounded monthly, compounded quarterly. So 0.065% divided by quarterly is 4 decimal places. 1, 2, 3, 4. Okay, I see the kind of day I'm gonna have. Cool. N, that'd be 9 times 4, which is 36 payments. Alright, so here you're going to take that 5.5 divided by quarterly, same exact thing. So this one's going to be 0.055 divided by 4, which should be 0.0138. And then here, 8 times 4 is 32 payments. Okay, moving on. Same exact thing here, 7%, annuity, cool. Here, they just want you to plug everything in. Use the future value formula to evaluate the indicated value. N is, I believe, which one of these is it? It's I don't remember if it's minus or plus. I think there was a minus in there. I think it would have been the future value is $40. 1 plus the rate. I is 0.3. I don't think is that going to be 0.03? Raised to the 49 divided by 0.03. Yeah, okay, that was the formula. And then you just gotta plug that in. Plug it into the calculator right over here. Just do 40 times, create the fraction. Once you have the fraction in the denominator, I'm gonna put 0.03. That's probably the easiest. In here, I'm gonna do 1 plus 0.03, raise that to the 49, and then in this fraction minus 1, and then you're telling me that my future value is going to be equal to $4,341.63. Cool. Yep, there you go. All right, literally the same exact thing, right? So if you do it like this, future, oh no, this one is the other one. This is when they switched it because you're looking for the payment. So I can say y equals future value plus the interest rate raised to the n, and then this one would also be equal to I. Switch the, oh, I messed up. I'm just showing off right now. If I make this equal to x, and then I say y equals 4120, I could literally look for where these two intersect. So n is 13, minus 1, I is 0.08, and down there is also 0.08. $191.67. Cool. Literally the same exact thing here, right? You're just solving for n. I can get rid of all of this. So my future value now would be 2,000, and my I is 0.2. Also down here is 0.2. My payment is 500, and I want to find out what it would be there. And then I want to see when this is going to be equal to $2,000. What does that look like? 3.88, so 4. You can also work backwards in it. Same exact thing here, very just solving for I. Explain what is meant. Actually, let me see. So my future value is going to be equal to $7,437 with my payments going to be 500. N is going to be equal to, what was that, 10? Snoop. 10. This is going to be my X. This is going to be the X minus 1. When does this equal 7,437? Let's see if this. I'm looking for a decimal. I'm looking for a very, very, very small point. Uh-oh. How many decimals do I need? Around to 2 decimal places. So what is that intersection? 0.09. Cool. Okay, explain what is meant by the ordinary annuity. That is the sum of all payments plus all the interests. No? A sequence of equal, when the payments are at the end of each interval, and then it's equal a new ordinary. Something about equal, right? Yeah. Specific type where all the equal payments are made at the end of each time interval. Definition. Recently, More Money for You offered an annuity that pays 5% compounded monthly. If 1,000 that is deposited into this annuity every month, how much is the account after 6 years? Okay, so let's see. Here, we're looking for how much is in the account. So you're going to make a deposit of 1,107. Alright, so I have the $1,107 deposited at 1 plus my interest rate, which here should be 0.0. Oh, I gotta first find out what that interest rate is going to be. So 0.051, what is I, not R, compounded monthly, which would be divided by 12, which means that my interest is going to be that number right there, 0.0043. So then down here would be 0.0043 raised to the 6 years. I believe this is going to be t raised to the 6 times 12 is 72 minus 1. That seems correct. Again, 72 because it's 6 years deposited every month. So I'm thinking this account will be worth $93,187.66. Where did I make a mistake? How much is in the account after 6 years? So is t equal to 6? No. Because it's 6. That has to be 6 times 12 is 72. 3,000. Oh, round to the nearest dollar. 87. Oh, 1.5. If this becomes 2.5, and if I change that to 2.5, and oh, that's so annoying. Oh my goodness, that's annoying. There it is, 93,000. So enter that into Desmos. Okay, you win. That was annoying. Oh, it's a part 2. How much of this was interest? Would that just be 1107 times 72? And then do 93,015 minus 79704. $13,311. $13,311 was interest. Yep. Okay, in order to accumulate enough money for a down payment on a house, a couple deposits $404 per month into an account, paying 6% compounded monthly. If payments are made at the end of each period, how much money will be in the account in 4 years? So let's go ahead and change this. What are they? Oh, let me just change that. So they're depositing $404 into the account, paying, what is that? 6%. So 6% monthly. That means you're I is 0.05 divided by 0.05, and the number of payments is going to be monthly. 12 times 4 is 48. So you should have $21,855, rounded to $56. Double clicked. $21,856. Cool. Acme Annuities recently offered an annuity that pays 4.5% compounded monthly. What equal monthly deposits should be made in this account in order to have $182,000 in that many years? So I'm just going to say that this is going to be equal to 182,123 equals X 1 plus, what is this? This is going to be 45 divided by monthly, so then that is going to be 0.375, 0.375 raised to the, I don't know, what's 12 times 18? 12 times 18 is going to be 216 payments, and then that should be the minus 1. I get rid of this. I want to know when y equals 182,000. We zoom way out, so I gotta go to 182,000. I gotta find that intersection. I'm looking for what monthly payment, so I should be in like the $548, and let's do 548.41. Yeah, cool. Otherwise, this would all give you a number. Divide both numbers by that. It gives you X. All right, beginning of first employment deposit $10 at the end of each month, earning 3% compounded each year. Taxes must be paid on the interest during. Find the interest earned each year during the first 3 years. Whoa. Okay. 1 year. Find the interest on the 1 year. Then the interest during the first period is that. Determine the number of. Oh, find the interest on. Okay, I get it. Alright, so let's clean this up. Let's just start all over. Oh, I needed that equation. This one. Alright, so is it a plus? Is it still a minus? Yeah, it's still a minus. Okay, let's see. We don't know how much is coming out, so we're looking for that. I know that I'm depositing $10 each pay period. That earns 3%, so 0.03 divided by monthly is going to be 0.025, 0.0025 raised to the 12, because it's 1 year, right? So that means that it's going to be $121.66 minus what would have been, 10 times 12, it would be $120. So the interest made during the first year is $1.66. The interest rate during the second year, so now that's going to be raised to the 24, which means that I would have $247 in that in my account. 247.03, right? I'll do 0281 minus 2 years of payment. That's 24 payments. That would have been $240. So I would have had $7.03. $7.02. What? $10. 24. The interest earned during the second year. The interest earned during the second year. Do I need to subtract the 166? 7.03 37028 minus 1.66. Did we earn $5.37? 5.37. Is that what it is? That's what it is, because the interest that was earned during the second year. I got it now. And now the third year would be 36 months. And that would give us $376. 376.21 minus 36 payments would be $360, which gives us $16.21. $16.21 minus the interest made during the first one, which was 1702, which gives us $9.19. $9.19. I was probably off by a penny. Minus 1.66 minus 5.37 is 18. Told you, off by a penny. Welcome to business. All right, Bob makes his first $1,600 deposit into an IRA, earning 6.6% compounded annually on his 24th birthday, and his last $1,600 deposit on his 39th birthday. 16 equal deposits in all. With no additional deposits, the money in the IRA continues to earn 6.6 compounded annually until Bob retires on his 30s, 50. How much is in the IRA when he retires? All right, let's delete. First thing is how much he's making on this interest rate. So he's depositing $1,600 into an IRA, earning 0.066 divided by how many annually? Divided by 1. So that means that his interest rate is 0.066. Divided by 0.066 raised to the, he made 16 payments, 16 equal payments. Okay. So it looks like he would have a total of 43,000. Does that seem right? 2,000 times 16. Yeah, that seems right, because he's gonna have just on deposits alone times 16. He'd have 25 grand in there. From there, earning 6.6% compounded annually. The amount in his IRA when he retires. No. So this is how much he has in his account as he's adding. Then it continues to earn compounded annually. That formula is, I believe it's the principal, $43,162.453 times 1 plus R, which is 0.066 raised to the number of years. He retires on his 65th. So would that be 15 years? You think that's raised to the 15? From your 40th to your 65th? No, 25 years. Your 40th birthday to your 65th birthday would be 25 years. So let's see, is his IRA then worth $322 and was that 29 cents? No. Okay, use the formula. First find the future value of the IRA when payments increase. Then use the formula with P being, I did that. So let me just view an example. Let's see where we made a slight mistake. I'm probably off by very small. 1 plus 0.06 raised to the, okay, they did 26. Yeah, so he did hours of 16, equal payments, 1 plus that divided by that gave him that with a lot more money there. I was 1,600, right? 1,600, yeah. 6.6%. We're good. Okay. That gives me that. Round to the nearest cent. 45. So then if I get rid of this, 27, now it goes to a 27. Oh, okay. 213, 322, 27. Still off. All right, let's go. I'm gonna put that principal 1 plus I raised to the n. Oh, then for me it should be 26. Should be 26 years. So let's see, 227, 401.54. 227, 401.54. Correct. Okay. Okay. So you can afford monthly deposits of $210 into a bank account that pays that. How long will it be until you have $5,000 to buy the boat? So then I could just say that y equals, what is it, 210 times times a fraction with a parentheses 1 plus what is 0.033 divided by 12 is this number, control copy, plus control V divided by control V, this number raised to the number of payments, so it's how long. Well, monthly payments, we don't know what that's going to be equal to, so that's 12x. And then, is it minus 1? I believe up here should be minus 1. I go back to the home screen, and I'm looking to see when y is equal to 5,500, right? Zoom out a little bit. And how many months is it going to be? Let's see. What was that, 2.1? That's years though, right? That's years. So if I get rid of the 12, it should be just a little bit bigger. It should be 25 months. So 26 months. Cool. And two last questions. Use geographical approximation techniques or an equation solver to approximate the desired interest rate. A person makes annual payments of $1,000 into an ordinary annuity. At the end of 5 years, the amount of the annuity is at what annual nominal computing rate has this annuity earned? Okay, so let's just say that this has earned 585 point, 58.42. And then how many $1,000 into it at the end of 5 years? Well, we don't know what the rate is, right? So I could delete this and put X. I can delete this and put X. T is going to be 5, and it's paid annually. All right. So obviously it's a parabola. It looks like some kind of parabola. But we can't take the negative value. We can only do the positive value. So what is this x value going to be? Oh no, this needs to be 58, 58-42. I'm just zooming in to get as close as I possibly can. What is that? Oof. How many decimal places? So can I put 0.08? 0.07? No. What is the annual nominal computing rate has this annuity earned? How do I do that? That's what I did. That's what the question had. 58, 58, 42, 1,000, 1 plus x, end of 5 years. And then you're just looking for the intersection. Oh my goodness. Oh my goodness. That's 7.93%. Oh my god, that was brain fart. There we go. In a percent. There it is. Next question. Okay. Same information. When would an ordinary annuity costing quarterly payments of what? Quarterly payments of 648.91 at 5%. So that's going to be quarterly is 0.05 divided by 4 is going to be 0.0125. 0.0125. How many years? Let's put that into the 4x. And when is y equal to 6,300? Oh, snap. No, that's a different question. This is asking, when is this going to be more than y equals 6,300, 1 plus compounded quarterly, so that should be the same 0.125 raised to the 4x. These are my two. Uh, 0.12525. So this is the equation going there. This is my second equation going there. Where's their crossover? Somewhere there, right? Right there. Round to 1 decimal places. It would take approximately 2.6 years. To make this a little bit easier to see, just get rid of the 4. Oh, it's still going to be the intersection. And then that'll be nope, needs it. 4 and 4. Cool. But yeah. Awesome. And that is homework 3.3, future value and annuity. 33 minutes. Best of luck.